examples and also the assignment for this chapter on course view. So you can download it from here and also here. Okay. So today I will go through this example. Okay, we have distribution circuit 12.47 kilovolt. This one is fed by 138 kV transmission system. The transmission system is represented by a Thevenin equivalent circuit on high voltage side of distribution transformer. The short circuit capacity at the high voltage side of the substation transformer is this one. Compute the following: the corresponding short circuit current, equivalent impedance in ohms, and also equivalent impedance in per unit. Okay. So for this problem, we have distribution circuit and also the transmission, right? So the transmission is represented by this voltage source and this impedance. Okay, suppose this is ZS and VS, something like this, and then this go through the distribution circuit, and it start with transformer. So this is 138 kV, and this is 12.47 kV, something like this. And this part, this is the Thevenin equivalent circuit. And this represents the transmission system. And then from the transformer, this is the distribution system. Okay, we measure the short circuit capacity at the high voltage side of the transformer. So we measure the short circuit capacity right here. SSC, something like this. This is the short circuit capacity, and this one is 5,000. Okay, we also have angle, something like this, and this is three-phase short circuit capacity. Then we need to calculate the short circuit current and also the equivalent impedance, which is this one in ohm. So this is single line diagram. If you want to draw the circuit diagram, you can draw it like this. So suppose we have, okay, this is the voltage source and impedance ZS, VS, and then ZS, something like this. And this will go through the distribution circuit, right? And when you want to calculate the short circuit capacity, short circuit current, so there is a short circuit right here from this terminal to this terminal, and then this is the short circuit current, something like this. So okay, this short circuit current, and then we have equations like this. The short circuit capacity, this is three-phase, equal what? because PS is at the rated. Okay, PS is the rated value, and this is line to neutral, right? This is line to neutral, so you multiply by 3. You have 3 phase. So you can write something like this. This is root 3 VS rated, and then line to line. And this is just only the magnitude. The angle is 0 degree. And then ISC conjugate. So you will have the equation like that. Okay. You have the equation like that. So the short circuit current is SSC conjugate divided by root 3, and then V rated. I just want to make sure that this is the angle is 0. Okay, short circuit capacity is this one, and then root 3, and then the line to line rated voltage is 138. So you will have this 20.92 angle minus 85 degree kilo amp. So it means if there is a short circuit right here at the high voltage side of the transformer, the 3-phase short circuit current would be around 21 kilo amps. Okay, any question? Then, okay, we have the short circuit current, so we want to calculate this impedance. This impedance, it can be shown that, okay, the current is equal what? This VS rated line to neutral divided by ZS, right? The current equal this one divided by this one, and this is line to neutral at the rated. So, okay, line to neutral. If you don't like line to neutral, you can use the line to line. Yes, rated line to line, but you need to divide. Okay, set the angle to 0, and this is just only the magnitude, and then divide by root 3. Right, line to line divided by root 3, you will get line to neutral. Divided by ZS, and this is the short circuit current. So we will have this equation. ZS equal V rated line to line is 138 divided by root 3 and divided by the current. So the equivalent impedance would be 3.81 angle 85 in ohms. So any question?
Okay. Why are we using 3-phase?
What?
For the short circuit capacitor, why is it 3-phase?
Why is it different? It is the definition.
Okay.
If you do not say anything, it is 3-phase. Then we try to calculate the base. Z base. The impedance base is E base square divided by S base. And we calculate the base here. Calculate Z base here. At the high voltage side of the transformer. Because this impedance is referred to the high voltage side, right? The impedance ZS is on the high voltage side, so we need to divide this by Z base on the high voltage side as well. V base square is 138 square divided by S base, which is 100. This is given. So you will have this impedance in ohms. ZS in per unit equals ZS divided by Z base. So you get this 0.02 angle 85 degree in per unit. So any question? Actually, if you try to calculate the short circuit capacity, let's see, this is 3 phase, and this is 5,000, right? Angle 85, this is MVA. Okay, this is in real unit. If you want to have the short circuit capacity in per unit, you have to just divide this by 100. And this would be what? 50. Per unit. Okay. You can see that ZS, okay, this is just the magnitude in per unit would equal 1 over short circuit capacity, and this is 3 phase and also in per unit. So it is 1 over 50, and this is 0.02. Okay, so in per unit, the impedance is just 1 over the short circuit capacity in per unit. I have already shown you this, right? Because we already talked about it. Today we will talk about how to calculate the voltage at the load. Okay. So when the load draws the current from the supply, the load voltage will fall below or rise above the open circuit voltage Vs. And suppose we have this single phase representation. Okay, this is a single phase representation. The source voltage is Vs, angle delta S, and this is R and X of the distribution feeder. The load current is IL. The load voltage is VL, and we fix the angle of the load voltage to 0 degree. The power demand PL and the reactive power demand is QL at the load. If you draw a phasor diagram from this circuit, you have this one. PL angle is 0 degree. This is the reference. We set the angle of the load voltage to be 0 degree. This is the reference. Then we have voltage drop across RS and also XS. The voltage drop is what? RSIL, and then XSIL. this is RSIL. Okay, this is RSIL. So R is real number, right? Suppose the load current is this one. This is IL. And the angle here is theta L. This angle is just the power factor angle. Okay, this is load voltage and this is load current. So this is the power factor angle or at the load. RS, this is real number. So this and this is parallel. This and this is parallel. But this is XSIL. This one is XSIL. So the voltage across the inductor lead the current by 90 degrees, right? The current lag the voltage by 90 degrees for inductor. So the direction is this 90 degrees. So this is the voltage drop across the inductor XSIL. And then you can find the source voltage Vs, which is this one. So because there is a voltage drop, across the resistance and inductance, so the load voltage and the source voltage are not the same. The magnitude are not the same, and the angle are not the same either. Okay, the voltage drop, you can calculate the voltage drop as represented by delta VL. This is the voltage drop, delta VL. Delta VL is just RSIL plus JXSIL. This is delta VL. You can just write delta VL into, separate them into what I want to say is the real part, which is delta VLR. This is the real part, and the imaginary part, delta VLX, something like this. For constant impedance load, we talked about constant impedance load last time. The load impedance will be constant, so it means ZL is constant. ZL equal V0 squared divided by S0 conjugate. I think I did not tell you, but okay, if this is line to neutral, this would be single phase. Okay, if this is line to neutral, this would be single phase. Okay, this is maybe single phase representation of three phase. Okay, be aware of this. When you do some calculation, you have to think about, okay, this is line to neutral or line to line or single phase or three phases or something like that. The voltage drop is delta VL is voltage drop. It is Vs minus VL or Vs minus ZL divided by Zs plus ZL Vs. Okay, this comes from the fact that the load impedance is constant. So this is Vs and this is Zs, and then this is ZL. So if this is constant, you can find VL. VL would be VL would be ZL divided by ZL plus Zs and then Vs, right? This is the voltage here. The voltage here is ZL divided by ZL plus Zs and then Vs. Okay, this is the voltage VL. then do the calculation, you get this, and just substitute this one into this, you get something like this. This is the voltage drop for constant impedance load. So I think it is easy to calculate. For constant impedance load, they will just tell you that okay, the nominal voltage at the load is, for example, 547 kilovolt, something like this. This is nominal voltage at the load, and they will tell you okay, the power is maybe 10 kilowatt, something like this. The reactive power is 2 kilowatt, something like that. The problem will give you something like this. Okay, this is the nominal voltage, this is P and this is Q. Okay, you have to know that this P and this Q is the load demand, and this occurs when the voltage at the load is 12.47. If the load voltage is not 12.47, this P and this Q will change. Okay, it means that if the voltage is 12.47, P is 10, Q is 2. If the voltage is not this one, P and Q will change. Right? Because this is constant impedance load. For constant impedance load, it means the impedance ZL is constant, but P and Q will vary when the voltage varies. Last time we talked about that, we say that okay, P vary with V square, and Q also vary with V square for constant impedance load, right? This is not constant power, so P and Q can vary. Okay, P and Q can vary, it means S can vary, but Z is constant. ZL is constant. Then we have constant impedance load. Oh, sorry, constant current. Constant current means the current is constant. For this problem, current is IL. So it means the load current is fixed, constant. Constant current is, we have this thing, this voltage source, and surface here, and we have load. This is load. Constant current. Constant current. Okay. The current is constant, the load impedance ZL is not constant, but the current I load is constant. So I load equal S conjugate divided by V. When we talk about load, usually we will say that okay, nominal voltage the same. Nominal voltage is 12.47 kilovolt, for example, and then this P is what, 10 kilowatt, and then this Q is 2 kilowatt, the same as that load. But for this time, the current is constant, so it means P will vary with V, and also Q will vary with V to the power of 1, right? That's how we talk about this. Okay. P and Q can vary if the voltage change, but the current IL still constant. Current IL still constant. The voltage drop is delta VL. Delta VL equal Vx minus VL, and this is ZSIL. Okay. The voltage drop is just, this is V drop. It's ZSIL. And if you substitute this into this, you get this. We may calculate the voltage drop by using this equation. Okay, this is ZSIL. This is the voltage drop. ZS is equal R plus JX, right? Z equal R plus JX. And then IL is the magnitude and also the angle. Theta L is the power factor of the load. We fix the load voltage VL angle 0. This is the load voltage VL. The angle is fixed at 0. And the power factor would be cos theta L. The current IL is IL and then angle minus theta L, something like this. Because this is lagging power factor. Okay, and this is IL cos theta L minus JIL sin theta L. And do the calculation, you get this and this. This is the real part of delta VL. This is the imaginary part of delta VL. Okay, we have real part and imaginary part. Okay, this can be written as delta VLR plus J delta VLX. If you go back to see the phasor diagram, this is delta VLR and this is delta VLX. Okay, this is R and X, real part and imaginary part. Okay, the voltage drop will have component delta VLR in phase with VL and component delta VLS in quadrature with VL. You can see the phasor diagram like that. Usually, we just consider only magnitude. we just want to see that, okay, so suppose this is 1 per unit. What is this voltage magnitude? We may just care more about the voltage magnitude. So if only the voltage drop magnitude is considered, we can neglect delta V of x because it tends to produce only the phase angle change, not the magnitude change. So if you go back to this phasor diagram, you can see that this component will change the angle delta S, right? This component will have impact on the angle delta S, more impact on the angle delta S. This does not has a lot of effect on the magnitude or the length of this and this. Okay, this component delta VLS has a lot of impact on the angle. It does not have a lot of impact on the length of this and this. This delta VLR has a lot of impact on the length of VS and VL. Right? You can see that because the WLR is in this direction, it has a lot of impact on the voltage magnitude drop. The WLS has a lot of impact on the angle. So it means if we consider only the magnitude of delta VL, you can approximate delta VL by just keep only delta VLR and neglect delta VLX. Delta VLR equal RS IL cos theta L plus XS IL sin theta L. This is just the approximation. It will make your calculation easier. Okay, any question? Then I just want to talk about the voltage regulation. The voltage regulation is V no load minus V full load divided by V full load. Something like this. We talk about this for the transformer and also for the transmission line, and we still use the same equation. V no load minus V full load, this is the voltage drop, delta VL, and delta VL is equal to this one. Okay, actually this is V no load, Vs is V no load. Do you know why? Because if this is open circuit, it means no load, right? No load means open circuit. This voltage and this voltage are the same. So actually this Vs is just the no load voltage. When there is no current flow at all, the voltage here and here are the same. So this is the no load voltage is Vs. Full load voltage is just VL, the voltage across. And you can see that the voltage regulation also depends on the angle, the power factor theta L, cos theta L and sin theta L. Okay, any questions that you would like to ask? Next, we have power load. This time the load power is constant. So it means if you say, okay, this is the nominal voltage, this is P and this is Q. It means the power P and also Q is constant, does not depend on the voltage. P constant, Q also constant. So does not depend on the voltage. You may have a question that, okay, if P and Q are constant, the impedance set here is not constant at all. This load impedance can be changed according to the voltage. If the voltage change, this impedance also change. Okay, this is constant equal to S0. Delta VL is the voltage drop equal Vs minus VL, and this is ZSIL equivalent to ZSSL conjugate divided by VL conjugate. We want to find the open circuit voltage, which is Vs. Vs will equal VL plus, this is the voltage drop, Zs SL conjugate divided by VL conjugate. Vs is magnitude and angle. VL also have magnitude, angle we fix it to 0. This is Zs. Zs is Rs plus Jxs. SL conjugate is PL minus JQL because this has a conjugate. And VL conjugate is VL angle 0 degree. VL and VL conjugate are the same because the angle is 0. Then, okay, this is magnitude and angle. You can write something like this using Euler equation. Vs cos delta S plus J Vs sin delta S, from here to here. This is VL. For this, you can separate them into real part and also imaginary part. Do the calculation, Rs, PL, whatever. Do the calculation, you will have this and this. And then, okay, because this is complex equation, this is real, this is imaginary, real, and also imaginary, right? So you can separate them into real equation and imaginary equation. So we have two equations. How many unknowns do we have? Usually the source voltage is fixed. We fix the source voltage, but we don't know the angle. We do not know angle delta S. We also don't know the voltage magnitude VL. We do not know voltage magnitude, but we know RS, PL, XS, and QL. We know XS, PL, RS, and QL. So the only two unknowns are delta S and VL. So two unknowns, two equations. So you can solve this, right? In order to solve this equation, we want to know VL. So we can get rid of delta S by what? Cosine square plus sine square equal to 1. Right? sine square plus sine square equal to 1. So you square the first equation and square the second equation and add them. So you will get Vs square cosine square Vs square sine square. So this combine and you get Vs. And then this is okay, square of this plus square of this, you get this. So right now you have only one equation with only one unknown, which is PL. Okay, you have VL square here, and then this is constant, no VL at all, and this divided by VL square. Quadratic equation, right? Quadratic equation. So if you have something like ax square plus bx plus c equals 0, quadratic equation, how can you get the what is x? Minus b plus this b square 4ac divided by 2a, something like this. So you get two answers, plus and minus. And what is x? In the equation, x is VL square, right? In the equation, x is VL square. So make sure that this x is positive. You have to make sure that this one is positive. So it would be better if you just use this one. Okay, make sure that this is positive. Then you will have VL, and then okay, take the square root to obtain just only VL. Okay, any question? Maybe this may be too complex for us. We have approximation method as well. So for the approximation method, okay, again we can compute or calculate the voltage drop by using this equation. VL equal Vs minus VL, and this is ZS SL conjugate divided by VL conjugate. ZS is this one, and S conjugate is this. VL conjugate and VL are the same because the angle is 0 degree. Okay, you can have real part and also imaginary part. And then this is the real part and this is the imaginary part. Again, we can write the phasor diagram like this, and we can also negate delta VLS, similar to the thing that we have talked about. We can negate delta VLS, so the voltage drop becomes just only delta VL approximate by delta VLR, and this is the equation. Okay. So we can calculate the voltage drop easier by just using this equation, and this is just the approximate one. Usually we know Vs, we know this. Now this Vs, we do not know VL, we do not know. So we don't know the voltage drop either, right? But we have VL here. Sometimes, okay, if you can say that okay, VL and Vs may be approximately the same, so replace this VL by Vs. can do that maybe, but this is just approximation, so the result may be not so accurate, but it is approximation. The voltage regulation is given by this, so you just substitute the VL here and change VL to VS, something like this. Okay, any question? Okay, I have some just the remark. So for high voltage system, usually have high X over R ratio. High voltage, X is large, R is small. So the voltage magnitude are affected more by the reactive power. According to this equation, you can see that the voltage magnitude delta VL, this is just the magnitude, will be affected by QL if X is large and R is small. For high voltage system, usually R is small, right? The reactive power has a lot of impact on the voltage magnitude. Okay. But for low voltage system, the X over R ratio is low. X is smaller than R. The voltage magnitude are affected more by the real power. You can see this equation. If R is large, X is small, PL will have a lot of impact on the voltage magnitude compared to QL. Okay, any question for this? High volt system, reactive power has a lot of impact on voltage. Low volt system, real power, not reactive power, has a lot of impact on the voltage. The voltage drop would be large when the system resistance is large. For example, from this phasor diagram, if R here is large, there would be voltage drop will be large. Voltage drop is the change in the magnitude of the voltage will be large when the resistance is large. The voltage angle difference delta S will be large when the reactance is large. When X is very large, you can see that it has a lot of effect on the angle. Okay, any question? Let's talk about the example. So this is example 2. We have a 3-phase feeder with this impedance. The line-to-line voltage at the load end is this one. Total 3-phase power at the load is this. At lagging power factor of 0.8, determine line-to-line voltage at the sending end, power factor, copper loss, and real power at the sending end. I think this one is easy because it tells you the load voltage. The load the load voltage at the sending end is this one. So it makes the problem a lot easier. Circuit like this. This is VS, and we have ZS here, and this is the load. Say P and Q. Something like this. This is 6 plus J 20 ohm. The voltage here is 13.8. kV, but this is line to line, right? So divide by √3 to have line to neutral, and then set the angle to 0 degree. The load is 1200 kilowatt and 0.8 lagging power factor. This is my VS at the sending end, power factor at the sending end, copper loss here, and also the real power at the sending end. Why don't okay, first, the receiving end voltage is 13.8 divided by 3 angle 0 degree. You will have 7.97 angle 0. So this is this voltage VR. Then we try to calculate the load current IL. The load current is PR divided by this PR 3 phase divided by 3 VR and power factor, right? Power divided by P divided by power factor, you will have the apparent power, and then divided by VR. This is line to neutral. So this one should be 3. This is 3 phase divided by 3. The angle is arc cos power factor, and this is minus sign because lagging power factor. So you get the current like this. Then you can find the sending end voltage. Sending end voltage. VS is this equal VR plus ZLIL. VS equal VR plus ZLIL. So VS, this is VR, and this is ZL, and this is IL. You have with this VS. This is like neutral. So multiply by √3 to get line to line voltage at the sending end. Then we want to find the power factor at the sending end as well. Power factor is cos theta v minus theta I. For this problem, you have to include theta v as well, because this is not zero. If you want to calculate the power factor at the load, you can see that the angle of the voltage at the load is zero. So sometimes we just take only the angle of the current in the calculation. But for Vs, the angle of Vs is not zero. So we have to also have to include this as well. Power factor at the sending end is cos. This is theta v minus theta I, and you get 0.7 lagging power factor. Then calculate the copper loss. Copper loss is the power loss in the transmission line. So P loss 3-phase is 3 IL square RL, right? This is I square and then multiplied by R. 3, this is IL square RL, we get 70 kilowatt. The last one is real power at the sending end. Power at the sending end equal power at the receiving end plus the loss. So this is load power. Power here is 1200 plus loss. You get power at the sending end. This is power at the sending end. Or you can use this equation. PS equal 3 VSIL and then power factor. So 3, this is VS and this is IL and this is power factor. You will get the same result. So any question? Because this problem gives you the voltage at the load, so it is easy. Next problem. This one does not give you the load voltage, but instead it gives you the source voltage. For this problem, we have this distribution circuit. Determine the per unit load current, per unit load voltage, voltage regulation, and assume that the load is constant impedance, constant current, and also constant power. You need to determine the per unit current. So this is in ohms. So you have to convert this impedance into per unit as well. Okay, let's start with this. Set the base power to 250 kVA. Why this is 250 kVA? Because it is equal to the rating of the load. V base 1 equal 12 kilovolt. V base 1 on this side 12 kilovolt. V base 2 is 416 volt. 416 volt here. This side is medium volt and this side is low volt. Okay, this one is medium volt, but this one is low volt. Then calculate set base for each side. Set base is V square divided by S. This is set base 1 and set base 2 for each side. Then this is the line impedance. Line 1 is on the high voltage or medium volt. Line 2 is on the low volt side. Remember that this is ohms per kilometers. So we have to multiply by 3 kilometers as well, or multiply by 5 kilometers. Then we also have transformer. For the transformer, you can see that the base voltage and the rating of the transformer and the voltage rating of the transformer are the same, but the base power are not the same. So okay, the base voltage are the same, so you can neglect this. Z new equals ZO multiplied by S new over SO. This is impedance of the transformer. The new values of the base is 250. The base O value, which is the rating of the transformer, is 500 kVA. So you have this impedance in per unit. So any question? Then we calculate the total impedance. ZL equal ZL is the total impedance equals Z line 1 plus Z line 2 plus ZT. Okay, this is the combination, combine all 3 impedance. So you get this impedance in per unit. Then for problem A, this is constant impedance load. So for constant impedance load, this is set load, set load, and this is IL, and maybe BS. Okay. For constant impedance load, you can think that this impedance is constant. So the input load, first we try to find the load impedance. Z load equal V squared divided by S load. This peak voltage in per unit is 1 divided by 1 angle minus cos cos phi. Do you know why the voltage V load is 1 per unit? You can see that, okay, the load voltage is what? 416 volt, and the base is also 460. So this is 1 per unit. S load is what? 250 kVA. The base is also 250 kVA. See this? So this is also 1 per unit. Power factor is 0.8, lagging. So include power factor here. So the load impedance is 1 angle 36.87 degree in per unit. Then if you try to calculate the current, this is the current IL here, IL will equal Vs plus IL equal Vs divided by ZL plus Z load, right? IL, this is the current, is this one divided by this plus this. This is Vs, and this is ZL, and this is Z load. Get this. This is the current. Then, okay, VR is this voltage. VR in per unit equal Vs minus ZL IL. So this is Vs in per unit 1 angle 0. This is impedance ZL. This is current. So you have this. This is the load voltage VR in per unit. Then if you want to find the voltage regulation, you have 1 minus 0.9433 divided by 0.9433, you have 6%. Okay, any question? For problem B, this is constant current. Maybe a lot more difficult if you do not have this assumption. So first, just assume that the phase angle of the load voltage is 0 degree. So it means we try to assume that this angle is 0 degree. This angle also 0 degree, actually. This angle is 0 degree because we just said it. But we also assume that the angle of the load voltage is also 0 degree. So that it would be easier for us to calculate the current. Because if we do not know the angle of the voltage at the load, it is impossible to calculate the angle of the current at the load. IL, the load current, equal S divided by V. And then this is arc cos power factor. If you do not set this to 0 degree, you also have to add the angle of the load voltage here, right? But we just assume that the angle of the load voltage is 0, so we can take this out. So the current is 1 angle minus 36.87. The voltage at the load is Vs minus ZL IL. This is Vs, this is ZL, and this is IL. You get this out. Then calculate the voltage regulation. 1 minus this divided by this, we have 6.1%. Then you have an alternative way, just the approximation method. The voltage drop equal R I cos theta L plus X I sin theta L. We have already talked about this. Use the same equation. This is R I cos theta. This is this is X I, and then this is sin theta. So you get this in per unit. The voltage drop would be 0.0591. Then if you want to find the load voltage, it is Vs minus voltage drop. We have this. Then calculate the voltage regulation. We have something like this. If you compare, you can see that the voltage regulation and also the load voltage are approximately the same, so the approximation is good enough. Okay, any questions? Okay, the last one would be constant power load. For constant power, the power is constant. I equal power divided by voltage conjugate, and this is voltage. VR is Vs minus Zi, and just substitute this current into here. You have something like this. And then this is the value. VR in per unit equal 1 minus Z. This is S divided by VR conjugate. So for this equation, you can just move this into this. This is VR conjugate, right? Modify this by VR conjugate, you get absolute VR square equal VR conjugate minus this thing. Take the real part and imaginary part of VR. Okay, this is the real equation, this is the imaginary equation. This is complex equation, you can separate them into real and imaginary. Then try to solve this equation. Combine the equation, try to solve it. You will get the magnitude and also the angle of VR. This is magnitude and this is angle. Calculate the voltage regulation, do the same thing. 6.8%. Then if you think that this method is too complex, there is still approximation method. Okay, that we will talk. We have already talked about this, right? Approximate the voltage drop by P plus XQ divided by voltage. This is P and XQ divided by 1. The voltage drop would be 0.0591. Calculate the load voltage, you get this, and this is voltage regulation. You can see that the voltage regulation and also the load voltage are just approximately the same, so the calculation, the approximation is good enough. So, any question? example 4. So we consider this is three-phase low volt secondary system for 16 volt secondary system with balanced constant current load A, B, and C. Determine the total voltage drop in one phase of the lateral by using the approximate method, and determine the real power, relative power, apparent power, and load power of the distribution transformer. So we have distribution transformer like this, and we have three loads: load A, load B here, and load C here. And this is the impedance of the line. So load A draws 30 amps unity power factor, load B draws 20 amps, this is the power factor lagging, and load C 50 amps, power factor, this is the power factor and lagging. From this example, we also have to assume that the phase angle of the voltage at each load is 0 degree. So because this is constant current, you can also make this assumption. The voltage drop, this is the voltage drop due to load A, and you also have voltage drop due to load B and due to load C as well. So the thing is, because we have three loads, load A, B, and C, so we can take something like superposition. First, we calculate the voltage drop due to load A first, and then we just don't care about B and C at all. After that, we calculate the voltage drop at load B. We just take out A and C, something like this. So this is the voltage drop due to load A. Load IA is 30, and this is RA and cos theta A. This is RB. This is XA and sine theta A. What is R and X? R and X is just the impedance from here to here. Then you have, okay, for load B, this is current IB, RB, and then cos theta B, and XB sine theta B, something like this. What is R and XB? B is here, so this is R. R should be this one plus this one. X should be this plus this. Right? So R would be 0.15 and X is 0.03. 0.15, 0.03. Voltage drop due to load C, the same, but this time RC and XC would be RC and XC. Okay, you have to include from the transformer to here. Okay, RC and XC because the load is located here. So after this, you will have total voltage drop equal voltage drop due to A plus voltage drop due to B plus voltage drop due to C, and you get this. This is the total voltage drop. So I confused. What is the voltage drop? Can you just tell me what is the voltage drop? voltage drop is measured before and after, right? Before means when there is no load at all. After means when the load is installed. So this is the system. Before means no load. Okay, before means there's no load. So this is Vs. So the voltage along the line is also Vs, right? No load. So the voltage, there is no voltage drop, no current flows. The voltage along the line is Vs. Then you add load, right? You add load. The voltage drop is the difference between Vs and the voltage when there is a load. It also means that okay, when you say A plus B plus C, the voltage also depends on the location. Where is this voltage drop? Where did we measure this?
The end?
Yeah, at the end. Okay, if there is only one load, Vs and then Va, the voltage drop is Vs minus Va,
Yeah.
and this is here. How about this voltage? What is this? Yeah, same as Va. Okay, the voltage, okay, there is some current flow here, right? But the current flowing here is 0. No current flow because this is open circuit. Current flow is 0. But the current flow from this source to Va. And from here to here, no current. So the voltage along this line is the same. Then when you add B, this is VB. This is not VA at all. This is VA half. Because when you add this load, the current flow from here to here. This is original current IA, I mean this is IB. Right? This is the current flow to this load, and this is another current flow into this load. So this voltage will drop more. Voltage A will drop more because we add B. We drop further than the one that we calculate. But this is still VB because no current flow here. If you add here another load, it is C, and this current IC will flow from here to here. So this VA will drop more, VB will also drop. The location that we measure this voltage drop would be at the feeder end at the C. Because at the location C, it will include the effect from A, B, and C. Right? At this location, the effect include this, current this, and also this. Any question? Problem B, determine the real power, reactive power, apparent power, and also the load power factor on the of the distribution transformer. Okay, so determine the power here at the transformer.